lectures we will talk about Sobolev spaces, but we will discuss only very introductory material, and mostly we will be talking about only a couple of spaces, even though there are many of them. And why Sobolev spaces play an important role in modern partial differential equations? The reason is they provide a natural setting for boundary value problems. And here is an example of the simplest boundary value problem. We have a Laplace equation in domain omega. Omega is bounded domain in Rn, and here we have some boundary conditions, and such a problem is well posed, so which means that solution exists, unique, and continuously depends on data. So the small, if we slightly change data, the solution will be changed slightly. And if function psi here is continuous, and if we assume that the boundary of domain omega is smooth, for instance, if it is C1, we can talk about classical solution. So classical solution is C2 in the domain omega, because Laplacian is differential operator of the second order, so we want to have continuous derivatives up to the second order, and our function must be continuous up to the boundary. And when we were talking about classical solutions, we know that it's easy to prove uniqueness. For instance, we can use the maximum principle, but it's not that easy to prove existence, even for such a simple problem. There is a Perron-Poincaré method, and it's kind of very long. And now let's look at this problem again. So what if function psi here is not continuous, or differential operator is more general, so we cannot even guarantee that we will be able to find classical solution? So in that case, we can consider a wider class of solution. So we can drop this regularity requirement of function to be C2, and such solutions are called weak or generalized solutions. And we still must keep the well-posedness, so we still must consider problems where solution exists and unique, and in some sense small changes in data results in small changes in solution, but no regularity requirement, at least at the first step. And when we have such a weak solution, we then can think about regularity and see if the solution is indeed classical. And what is the advantage of such a point of view? Then we can it's not hard to prove, for instance, existence, but because we can use the machinery. Of course, if you know the machinery, then you can use it, and it includes tools of the functional analysis. So specifically, some Sobolev spaces are Hilbert spaces, so we can enjoin the properties of the Hilbert spaces. And here, just a quick reminder, so Hilbert space H is a vector space with an inner product such that the norm, which is induced by this inner product, turns H into a complete metric space. And the second, we can use variational setting for obtaining existence uniqueness results. And indeed, when you try to find a minimum of energy functional, we cannot expect that solution will have a certain number of derivatives, will be of class of Cm, say, in omega. And regarding this example, it is known from calculus of variations that Laplace equation is the Earth equation for the Dirichlet functional. So this is the functional, right? And solving problem 1 is equivalent to finding minimum of this functional among functions that satisfy this boundary condition, right? And it is known that the minimum is achieved on the solution of the problem 1. And as I mentioned, it is not guaranteed that this minimum, which is called minimizer, is in the class of C2. And what is a natural space for this minimum? It is this specific Sobolev space that people in the literature you can find notation as W to 1 of omega, or it could be written as 1, 2 of omega, or 2 and here in the parentheses 1, or H1. So what is H1? And before I erase, I need to fix the Poincaré name. So now that's good. So let's look at the definition of the space H1 or W21. I used here notation W21, so it's easy to explain the meaning. So U belongs to the space. It means that U itself belongs to space L2 on omega, and exists weak first order partial derivatives of function U, du dx j, where j runs from 1 to n, and we're talking about domain omega in Rn. And all these partial derivatives also in L2. Right, so here, just for comparison, I am giving a definition of more general Sobolev space. There are still more spaces, but if we look at the space WPL on omega, where P is from 1 and less than infinity, and L is a positive integer, so we say that U belongs to WPL. On omega, it means that U itself is in LP and exists weak partial derivatives up to the order L. So I use here alpha. Alpha is multi-index, and all these partial derivatives, weak partial derivatives, must exist and also be in LP. So here you can see that this 2 corresponds to L2 and 1 corresponds to the order of partial derivative. I will remind you in a minute the definition of weak derivatives, but before that, let's make a few remarks. So if we take here L as 0, then we will be just talking about LP itself. This space is WPL is Banach, which means a complete vector space with norm. And here just I'm showing the standard norm in WPL. And since our definitions involve LP, the space LP, so here I'm just reminding you the definition that of the space LP, when P is less than infinity, and it is a space of the big measurable functions on omega for which the norm is finite and it is a Banach space, and also we will need another definition of LP log. So it means that for any bounded strictly interior subdomain omega prime, F belongs to LP on omega prime, right? So here I just made a picture of domain omega, and here omega prime is bounded and strictly interior subdomain, and F belongs to LP on omega prime already. And just to comment that this space is not Banach. So now let's recall what is the weak derivative or generalized derivative. We've talked about this in video 16. So how we can approach the idea of weak derivatives. So initially suppose that we have two smooth functions, so f from C1 in omega and g that is C1, but also g has a compact support in omega. And then we can consider such integral partial derivative with respect to some xj. Again, so omega is a domain in Rn, and we can look at this integral as a divergence. So it's this integrand as a divergence of vector f, which has the following structure. So it has 0 everywhere, and on the j's place it has this product f j, and then using one of the versions of the Stokes theorem, right, from this divergence theorem, we can write that it will be a dot product of f and nu, where nu is the outward normal. So from integral over the domain, we can go to the integral over the boundary, and then since f has this specific structure, we will get just f g and jth component of vector nu, which I wrote here as nu j. And then if we recall that function g has compact support in omega, then we can see that the integral would be 0. And now if we look at the beginning and at the end, we will see that this integral is 0. But here in this integral we have a product, so those are smooth functions. We can just use the product rule and then move one of the integrals to the other side. So we will have that integral over omega df dxj g equals negative integral f times g dxj, right? So this is kind of the main idea. And now let's give the formal definition for weak derivative for a function u from L2 log, right? So function v from L2 log of omega is called the weak partial derivative of function u from L2 log of omega, and notation we use for derivative v equals di for u if the following formula holds for any function phi which is infinitely differentiable and has compact supports from any test function, right? That's what we called it. And here again alpha is a multi-index, and so here is the notation for just explanation of what the alpha is, right? So we have seen this formula. So I wrote the definition for u from L2, but of course instead of 2 you could put here, say 1, for instance, instead of 2 in both places, and so on. Okay, so we but I put 2 because we mostly will be talking about W21, as I already mentioned. And so we can notice that phi here has a compact support. So even if omega is not bounded, if it's Rm, anyway, we can think of these integrals as integrals over a bounded domain, because basically phi has a compact support, so we will be integrating over this compact. And also, if we, in this formula, we can notice that if we take first derivatives, so then our formula will look exactly like this formula that we originally obtained for smooth functions. It will be exactly the same formula. So some remarks. We have to mention that weak derivative is a derivative in a domain, not at a point, because we are dealing with function from L2, so we're talking about some classes of functions that can be changed on a set of measure 0. So it's a derivative in a domain. And obviously, if instead of omega we will take its subdomain, smaller domain, then derivative would be, they will coincide. And also, as I mentioned, that if we take a function u, if it's sufficiently smooth, because we will get here the same formula, so classical derivative and weak derivative or generalized derivative, they all will coincide. And I want to mention some properties. First is uniqueness, so weak derivative is unique. If we just, in the sense of the definition that was given, it also enjoys the linearity property as usual derivative, but there is some unusual property, right? For classical derivative, if, say, a derivative of higher order exists, say second order derivative, then we know that first order derivative exists, so low order derivatives exist. But with weak derivative, it's not the case. So from existence of higher derivative, it doesn't follow existence of low derivatives, and I will show you examples. Let's consider a few examples. So here I copied our formula for computing weak derivative, and so here phi is infinitely differentiable function with compact support, and u and its derivatives, they should be from L2 log. So, but we will consider first one-dimensional examples. In the first example, let's take u to be equal x on the segment 0, 1 and 1 on between 1 and 2. And the question we're interested in whether weak or generalized derivative exists, and if it exists, find it. So we will rewrite this formula, but we will rewrite for first derivative, but we will rewrite it backwards. So first we will write this side. I wrote it here because we know how to differentiate function phi. It's smooth, and our goal is to figure out whether this function exists as L2 log function. So we start with this expression, integral from 0 to u of x phi prime dx. Then so we want to find something this function if it exists. So then we can rewrite this using the formula. It will be integral from 0 to 1 x phi prime dx plus integral from 1 to 2 phi prime dx. And then we will compute the first integral by parts. So it will be x phi, substitution from 0 to 1, minus phi of x. And here it will be just phi evaluated at points 1 and 2. And phi evaluated at point 2 will be 0, since phi has compact support, and this is a boundary point. And then from this one, when we plug 1, we will get phi at 1. When we plug 0, again, due to the fact that phi has compact support, it will be 0. And this integral we can rewrite, and we can write minus phi prime, then phi prime phi at 1, and phi at 1 and phi at 1 will be cancelled out, and we will end up only with this integral. So our goal is to try to rewrite this integral in this form. So we can so in this case we can write integral from negative from 0 to 2, and here we can we need to find a function that is equal to 1 at the interval 0, 1 and or segment 0, 1 and 0 from 1 to 2. So that would be an indicator or characteristic function of the interval segment 0, 1. So it will be 1 when x belongs to this segment, and 0 when it is outside. So if we look at this function, this indicator, this is a function from the right space, right? This is L2 log function. So in this case, we were able to find the derivative, and that would be the indicator function. So now let's look at slightly modified function. It's example 2. If we slightly lift this part, so we put, for example, 2 instead of 1 in this formula, and then let's try to do to repeat the same steps and try to see if we will be able to find the derivative. So again, we look at this formula, right? We write it backwards compared to the original. So integral from 0 to 2u phi prime. Now then we can split it into two integral from 0 to 1, where we put x, and from 1 to 2, and we have to put now 2. And again, we will use integration by parts for the first integral, which results in these two terms. And then from the second term, now we will have phi evaluated points 1, 2, and multiply by 2. So repeating the same steps, we will get from the first term, we will get only phi at 1, copy integral, and here we will get minus 2 phi at 1, because phi at 2 will be 0. And finally we have phi at 1 and minus 2 phi at 1 will result in negative phi at 1 minus this integral. And now the question is it possible to rewrite this expression somehow in this form? If it is possible, then we can find the weak derivative. If it's not, then we cannot. So we're trying to think if it's possible to write here u prime from the needed space, and the answer would be no, it will not be possible. And we can show this by contradiction. So first, assume that such u prime exists. So we can write it then to log. And now consider a sequence of functions phi k functions from C0 infinity on this segment, and such that phi k at point 1 equals 1 and maximum of phi k, each phi k is 1. And support of each phi k is from 1 minus 1 over k, 1 plus 1 over k. So here I drew the picture. So this is my function u of x, which is x, and then 2. And then we have a sequence of functions there here, phi k, right? So they are non-zero on the interval from 1 minus 1 over k, 1 plus 1 over k. Outside of this segment, they are 0. And then when k goes to infinity, we will be getting functions with smaller supports, right? They all will be somewhere here. And so what? So we took this sequence, and now let's plug phi k into our equation. So this would be left-hand side that we computed of the equation, and this what we are trying to get would be right-hand side. So if we plug phi k into the left-hand side, we'll get negative phi k at 1 minus integral from 0 to 1 phi k dx. So by properties of phi k, we know that phi k equals at 1 equals 1, so here will be negative 1. And when we plug, since phi k, if we want to look at phi k at the interval from 0 to 1, then it's non-zero only if we take here 1 minus 1 over k. So these two integrals would be equal. And then when we send k to infinity, when k will be approaching infinity, this integral will be approaching to the integral from 1 to 1. So that will be approaching 0. So the whole expression will be going to negative 1. So it was this left-hand side. And now let's look at this right-hand side, which, if we assume that u prime exists, so in that case we will get integral from 0 to 2 u prime phi k x, right? We're replacing k with phi k. And then we can, since phi k has this support, instead of integrating from 0 to 2, we can integrate from 1 minus 1 over k to 1 plus 1 over k. And here we'll have u prime x phi k. So since we know that u prime is from L2 log and phi k is bounded, then the whole integral will be approaching 0. So because when k goes to infinity, right, we're integrating from 1 to 1, roughly speaking, right? And since these two functions, one bounded, one is L2 from L2 log, then the whole integral will be going to 0. So what we obtained, that left-hand side approaches negative 1 and right-hand side approaches 0. So this is not possible. So from here it follows that such u prime does not exist. So in this case we have shown that weak derivative for this function does not exist. Let's consider one more example for the weak derivative. In this case it will be just two-dimensional domain, and here I just want to illustrate that a higher derivative, specifically here second derivative, may exist even if the first derivative doesn't. And in this example we will consider function u, which is sum of function of x and function of y on this square, and we take function u1 the same as we had in the previous example, example 2. And so from this example we know that du dx with partial derivative does not exist. And now we want to show that the mixed derivative, second derivative, does exist. So we just use the same formula. I copied it here, so it means that we want to compute second derivative of our function u, and using this formula we write that will be -1 squared integral over the square of the functions of the sum of function u1 plus u2 d2 phi, as we have in the right hand side. And then I will just honestly compute these integrals. I will split it into two. In the first I will keep u1, and in the second u2, and then in each integral we can switch to the iterated integral. So I can rewrite this integral as integral from 0 to 2 u1 dx, and then from 0 to 2 second derivative of phi. And similarly I can rewrite the second integral as an iterated integral. And what can we see? For instance, here, right? So here, when we integrate with respect to y, we will get partial derivative of phi with respect to x, evaluated at the point when y equals 0 and y equals 2, and those would be parts of our boundary of our square. So function phi and its derivative is 0 there, and since phi has a compact support, non-zero and compact support inside our domain, and so that would be 0. And the same thing happens to the second integral. So as a result we will get 0. So our second derivative exists and equals 0. So we are done with preliminaries. Thank you.